Okay, welcome. I'm Tony Olenek, President of Nascent Technologies Corporation and a member of the Board of Governors of AOCS. Thank you for joining us today for our presentation called Practical Aspects of Cosmetic Emulsions under the new Lamellar Gel Network Model, co-sponsored by the Society of Cosmetic Chemists. Today's presenter, Professor Ricardo Diez, who I'm very excited about having him come and speak. He is very passionate about the work he does, and I always manage to learn something each time I speak with him. Dr. Ricardo Diez is currently an adjunct professor at Rutgers University, where he teaches 2 courses in Applied Cosmetic Science and a Master's of Business and Science degree. Very interesting. He has more than 4 decades of experience in the industry in both consumer product companies like Procter & Gamble, Dial Corporation, and Chanel, and raw material producers like Mironol, Stepan, and Huntsman. He's obtained a number of patents in the field of raw material synthesis as well as consumer product technology. He teaches courses for the International Federation of the Society of Cosmetic Chemists and the Society of Cosmetic Chemists of the US group. He also teaches for the Center for Professional Advancement and has received numerous awards for his contributions to the personal care science. I am really very excited that he's with us today and look forward to listening to what he is going to present. Please write any questions for our presenter into the questions section of your control panel. We will address them at the conclusion of the presentation. Again, thank you for joining us, and I will turn over the presentation to Professor Diez.
All right, good morning, and thank you for being here. You can see on the screen the city where I live, the city of Toronto. And I need to say one thing. I was listening to Tony, and he said at the end, I received lots of awards. I'm like, he said that, I didn't write that there. But anyway, hey, thank you, Tony. It's always welcome. So anyway, you know, I can't believe how excited I am considering the number of people that is listening to this, because this topic of emulsions as physical chemistry is not precisely your regular stuff about natural products. Everybody wants to listen to that stuff. This is the real McCoy. This presentation is about the science that has driven the industry to the levels that we have today. So I'm happy to see that we have all these people willing to see what great people have done over the years. So here we go. Oh, I need to tell you another thing. I have 200 overheads. So anyone that has seen me before knows that the overheads fly on the screen. So if you blink, chances are you may miss 3 of them. If you sneeze, you probably miss like 400 of them. So I suggest that you just keep your eyes open, take a deep breath, because once I start is so here we go. Very good. Well, that's the titles. I don't need to show you the same thing. Okay, here. Now, there is lots of books and stuff about emulsions as a science. The problem is that if you go and consider this one of the many, and you read it, then the question is, how do I apply this to make an emulsion for cosmetics? And the reason for that difference is that, you know, cosmetic emulsions have one thing that separates them from the rest: viscosity. It will be difficult to find something there, whether it's for skincare, for color, that has no viscosity. And the need to build viscosity, which is something the industry figured out how to do years ago, makes these emulsions different from the rest. And it just happened that this model is fantastic because it has been built around how do I get viscosity. Similarly, if I say, well, I try to apply this model in an emulsion, let's say oil recovery or agricultural emulsions, where you don't need to have viscosity, it may be a different story. So this is just the food that you want to eat. So, okay, so I am quite sure all of us have seen this stuff, liquid crystal. Well, you know, you can read. So it's novel. This is new type of emulsion. So the question is, well, this stuff that we have since the 1900s, and this other one, but all we know this product. So this emulsion that have liquid crystals, because you know apparently it's new. So is it the same? So these liquid crystals, everybody talk. This is the same thing. You need to wait. So from the supplier side, we can see these days that, you know, just liquid crystal, there you are, liquid crystals, lamellar, more liquid crystals, lamellar. So everybody's talking about that. I mean, by the way, this means it appeared in Happy Magazine. So everybody, what is this? So what is this? It's very interesting. Well, you see, they all refer to the skin. So this stuff over here, I don't want you to believe that this is celery in a supermarket. This is a computer-generated image of the lamellar structure of the skin. And you have the free lipids and, the magic of nature. Talk about natural products. These are natural products for real. You can see how the fatty acid, the ceramides, and the cholesterol organize themselves in lamella. So this is fantastic. But I tell you one thing, so is my wife. My wife has all these shoes in a lamellar structure. And so the point of this is, so what's the point? So to try to tell me that I can make an emulsion with an lamellar thing because it's the structure of the skin, so what does it mean? So it doesn't mean anything really. So don't try to tell me that if I have an emulsion that mimics the lipids of the skin, I'm getting something. So no. So this is what happens. So this gentleman is, well, in case you don't know, is Newton. So let me ask you this. Well, I cannot ask you this because you're not going to be able to answer me. So the question is, were apples falling out of trees before Newton came with the gravity thing? Or they were not? And then one day this guy was sitting in the morning and said, oh, I'm going to invent gravity. And all of a sudden the apples start falling out of a tree. Well, we know gravity was there. He's the one that came with an explanation. The point of this stuff that I told you is that we have had maybe products with this before we came with Newton's explanation. Why that? Not gravity. And so the way to know if anything from an emulsifier, when you use it to a formula, it has this thing is with X-ray diffraction. So you see, say you put the product there, and here I'm going to show you this with this bottle. This is water. So if I put X-ray through this water, it's going to give me nothing. It's going to give me this, nothing. But if there is a crystalline structure, it's going to give me some peaks. The question is, which one of these two is a lamellar emulsion? Because they are not the same. You see, the peaks are not exactly in the same spot. So you see, what this means is that one thing is to have crystalline structures inside of a cosmetic product or anything, and another thing is to have a lamellar gel. So this is how it goes. I don't want to confuse you. Liquid crystals is like fruit. Lamellar is like oranges. So liquid crystal is a big word, and lamellar is a specific type of liquid crystals. And this is the structure, the oranges that we are going to use in our making of emulsions. So it happens that all these products, if you run X-ray diffraction, they are going to show a lamellar structure. So we have had these products on the market for a long time. The fact that we didn't know does not mean that the structures are not there. I'm making this point because all these days you hear, oh, these new emulsions, oh, these new emulsifiers. Oh, give me a break. We have had them for more than 100 years. Don't confuse the explanation with the nature of what is there. So if now I go into, well, okay, so these things have a lamellar gel network, what I just told you right now. One thing is to have liquid crystals, and another thing is that they are in a lamellar shape. Okay, we will see the answer to this in a second. Now, you know, all these products are called gel. So you have here a gel, gel, and gel, and gel. So are these also this thing that we're talking about? That is a category that is growing fantastically. I mean, the donuts is like 10 years ago, give or take. Now it's all over the place. So do they have a lamellar gel that go inside? Because they're called gels. Okay, so, well, if you run those two, you get nothing. Because in this case, the word gel had nothing to do with chemistry. The word gel had to do with a product category. It's lots of sense, lots of sense. I mean, we have had gel products like yellow pudding for a long time. So there is no structure in this product. They have no crystallinity. So what about this? Oh, yes, I forgot the next slide. This is it. So they have no crystals, but they have a gel network. It's not a lamellar, there's no crystals. So this, what they have here is a polymer that is creating a gel structure that is non-crystalline, it's amorphous. So these materials, you know, they're made with polymeric emulsifiers. So that's it. That's how they work. So you have the oil phase and it's stabilized by a polymer. There is no crystallinity. So what about this product? So if I run the X-ray diffraction through that, I'm going to get some crystallinity. So it happens that this product is a combination of two things. Some of the emulsifier is the stuff, it's a lamellar gel there. And also you have a polymer. It's a combination of the two. And these ones formulated with a combination of the two are becoming more and more popular every day. What happens, you see, is that this is the difficult one to understand. The other is the polymer, and God bless America. It does it by itself. It's a different story. So, what is this thing? What is this thing? Well, you know, this book, you can see there, Professor Love here. I don't know if he's listening to this or not, but this book published on the year 2000. Well, you see the date. Chapter 25. There is a fantastic thing. This guy from Procter & Gamble wrote the best summary I have ever seen. It's fairly new. Now, but it makes reference to 53 papers. Now, listen why this is here. What I try to tell you is this is a model that has been put together by this gentleman. It's a model. It's a combination of papers. And with the exception of 2 or 3 papers, none of this has been done by the cosmetic industry. The few papers were done by us a long time ago. The majority of the papers, if you look, have never been published in our journals of the IFSCC or the SEC. So what I'm trying to tell you is this is a great model in which the cosmetic industry is a great model for us. And the participation of the industry, either by work or by publication, appears to be unrelated to us. Now, I have to tell you, if I get up tomorrow morning with an idea, I may call Tony to say, what do you think of this idea? And he said, oh yeah, it's great. So let's do experimentation. So we have an idea, we create a model based on our ideas. This is not the case. This is a model that has been put together by bits and pieces as a puzzle. So this is not that this guy wake up in the morning and say, I got this idea. And as a result, this is a puzzle where some of the pieces are missing, because I just told you, it's based on collecting information. The good thing about this model, once you understand it, is that it allows you to control everything that you want to control in a cosmetic emulsion. Okay, I put you an example. It happens that these products, all of them fit within what the model says by luck. This product, I am quite sure, nobody developed this product thinking of the model. So what this means is that when I get this formula, because I know the model, if I know the percentage, I can translate automatically to the physical structures. So I know the model is telling me that thing over there inside the product, it is no molecules like, fish moving around. No. Some of these ingredients create these structures. So they do it. They say, I like you, I want to do this. I don't like you, I'm not going to be with you. So the model translates chemistry into physics. And now this physics is what allows you to control that. So I can go from this formula to this, like that. But man of speaking, you know how humble I am, okay? All right. Now, it gets better. Because assume for a moment that this is the image that you see under the microscope, polarized light. And then when you apply it on the skin and you do chicky, it's going to start to evolve. And this is the final thing that is left of your skin. So the chemical composition brings the physical structures that start to evolve. And guess what? What you leave on the skin at the end is not only how it feels, it's key for hydration and for the delivery of active. So this is a fantastic model, So now, not only that, you can change the property. So I made this product, and by the way, I know what I'm talking about because I have, I have done something very similar to this product using the model. It is fascinating. So now, for example, if I want to change anything, I want to have more hydration, or I want to make it thinner, or I want to make it thicker, it's not going to take me 27 years to do it, because I know how to change this, how to change that to get what I want. Very, very, very fast. So there are other products that don't fit. There's many products on the marketplace that are emulsions, and they don't fit within the mold. So it has been made not following the rules. I want to give you the rules in a moment. And therefore, if you take one of these products and I want to change it, it's too viscous to this and that, it becomes more difficult. Because right now, they have been put together by other means. Because you see, this the story is, if you have the map, this is the model. You have a map, and it tells you how to go from A to B. You know how to go. This is the map of Toronto, I think. Okay, there you are. On the other hand, I think my wife is not listening to me. She doesn't like maps. She said, I'm going to go from here to there. It doesn't have a map, so I go all over the place. Maybe 3 days later, you get there. So the model is a map that helps you, but you need to know how to read the map, obviously. So now, when I teach this thing at the university, it takes 24 hours. I don't want to believe the students show up at 8 o'clock in the morning and they leave 24 hours later. It takes me 8 classes, 3 hours each. So this is not here to talk for an hour. I gave a reduced version last year of 6 hours. So I just want to tell you is, the top notes of what this is about. So how many methods we have on the on the industry to make creams and lotions? Number one is this one, which is very important. It's called mix and see what happens. And then that's what it is. So depending on how difficult the product is, the experience that you have, it may take you 3 days, may take you 2 years. And once you have developed it, then you hope that it's stable, because the last thing you want is you put the bottom of the water and sinks. So let me ask you, I can't believe this. So we have been making emulsions for 100 years. We develop something on the lab, and then we say, oh, God help us, the product needs to be stable. How is that? So this is like somebody developing an airplane, and then you say, I hope it flies. Don't you think that after 100 years, we should know if what we have developed should be stable? So anyway, then the other option is you copy a supplier's formula, which is very common today, especially, I'm not talking the large corporations, right? You copy a supplier formula. It happens that there's something you don't like. And they say, oh, I don't like this, I'm going to start changing it. And then so you go back to the other thing because you don't understand anything of what is going on. So back to model number one. And then we have Griffin. Now, everybody knows about this gentleman. This was published, his method, in the first journal of our, the journal of the SEC. And that's the number of experiments he did, many. And this is a method that everybody talks about it. If you're teaching emulsions, you need to talk about it. I talk about it just to say that it's useless. And I tell you one thing, I give him credit, two things. Griffin did two fantastic things. He put ethoxylated emulsifiers on the market, unknown until that moment. But they were invented in Germany in the 1930s. The question is, they came the wars and they need to produce them, you need to use them. And he also came with this great idea that if you have two ethoxylated, you're using ethoxylated emulsifiers, blend two with high and low solubilities. Now, we all of us know about this method. This is the HLD scale, water soluble, oil soluble. So, water is one. And so when he created the scale, I guess he have water. So what is the oil that Griffin used to do his scale? Now, I know you can reply to me. So listen to what I have to say, because you need to know what oil he used. He didn't use any, no oil. Because you see, the method by Griffin is nothing else more than a water solubility. I mean, the method was used with other words by the German company GIF, that's what I learned. And it was just a water solubility scale. So I don't understand why we have built a great thing with decimals when it's nothing else more than a water solubility scale. He never used any oil. How can you say a balance between water and oil when there was no oil used? Yeah. So this model here, I'm doing fantastic. Look at that. I am supposed to be at 10, at 11:20. I can't believe how good I'm doing. Fine. So I need to slow down. I'm going to slow down. I'm going 1 minute too fast. So, okay. So this method from this gentleman, 2017, he hasn't invented, he put all the pieces together, is based on many papers, as I told you. Now, the ones that I show you here are the ones that I was familiar, that I read before I read this paper, this chapter in the book. And these are. Now, out of all these, and I have here 1, 2, 3, 4, 5 papers, one and only one came from the cosmetic industry. Is this one here? And this is one of the best papers I have ever seen. Unfortunately, that's what the industry was doing 40 years ago. That's not what we could do anymore. So this means that when I started working 2007, so it's 13 years ago, I didn't know about this model, I had no idea. So I was familiar with this and other papers. So what happens is that because I was learning from here and doing my own experiments, when this model came, I said, holy man, I understand this guy. I know because I have been doing some of that. So let's consider the first paper. This is Professor Friber, well, there you are, and at the year 1971. Watch. Whoopally. Uh-oh. So here's the first one that says this stuff that we have been saying that there must be some liquid crystals when we make emulsions actually do exist. And it has here the image to prove it to you. Remember, we're dealing with 50 years ago. And then he said, if I use 2% to make this emulsion, whatever was the content of the oil phase, so when I do all my calculations, it happens that I have a hell of a lot of emulsifier, much more than what I need to do to cover the oil phase with just one layer. So it looks to me I have lots of layers, and the lots of layers are about 0.3 microns. So the emulsion is 1 micron. So this is about 1/3 is made of layers. Now, he never explains how he did the calculations. I don't like this guy. So I say, I'm going to do it. So here's the story, man. It looks like the virus, for God's sake. It's not a virus, huh? So this is how it goes. So you make an emulsion, 20% mineral oil, 4% emulsifier. And an emulsion is 1 micron. So the question is, what will be the minimum amount of emulsifier that you need to cover completely all those oil droplets with emulsifier? So I have had this question for years and years and years that I'm teaching now, and there has only been 3 students ever of the hundreds that I have had that have been able to come up with the answer. So I'm going to do the calculation for you. I need to do it very fast so you can look at them slowly on the recording. Okay, so the first thing, you need to transform 20 grams of oil of 1 micron radius into the total surface area. Oh, look at that, 62 square meters, a hell of a lot of meat. That's like 620 square feet. And then we know what is the size, the diameter of the emulsifier, which is going to be, I'm going to be sticking emulsifiers all around. So now what I do is that I divide, that's the number of molecules that I need to cover the surface, and then say, oh, hello, this gentleman, Italian gentleman, is avocado. So I transform the molecules into moles, and then I multiply by the molecular weight. I assume this is the average molecular weight, and I get 0.3 grams of emulsion, and holy guacamole, I'm using 4. Hey, what happened to the rest? What is the rest of the emulsifier? So, according to the calculations, I did the same thing the other guy did in 1970. You only need this small amount. What happened to the rest? What is the rest? It's gone? Well, this is where this guy is fantastic. I have a smart, this guy is still alive. I'll show you his name. He has a great number of papers, is still active. He is a genius, man. So it takes this, by the way, the original paper is in Japanese. Fortunately, the graphs is, well, the graphs are normal, and the writing of the graphs is in English, so I could figure this out. So anyway, that's his emulsion. I'm talking you, just get the concept, right? Again, no viscosity. So to get viscosity, use an old trick. In 1983, we already know, just put a fatty alcohol and the viscosity goes up. So according to the model by Griffin, the reason why the viscosity goes up is because the fatty alcohol that you add in the mineral oil, in the oil phase, thickens. Upon cooling, thickens, and that's why you get viscosity. But then it looks under the microscope. Remember, this is a long time ago. And it noticed, well, you have seen this now many times, but you're talking about years ago. This was kind of novel. So he noticed that there is something around the oil, very similar to what Professor Previous said in 1970, and that's what he called it. That's the, that's the only thing that is in English on the paper, the title. From Cow, this guy is a genius. Now it doesn't work at Cow anymore. This guy's really something. So he called this thing secondary droplet. Oh, there you are. I'm not inventing anything. So it didn't call it liquid crystal, it called secondary droplets. So what it's going to do, I said, what the heck is this made of? So it just centrifuges the emulsions to separate them. And what it does now, it takes the secondary droplet, that stuff that he has separated, and it goes under the X-ray, and looks and sees this. Holy crap, look at that. If you multiply this number is double that number. And that automatically means, for anyone that has ever done crystallography, that you have a lamellar structure. This is his own writing. So there you are, his shoebox. He knows that it has a lamellar structure. So those crystals are round, they're in a circle, but they are forming this structure. And there you are, I give you to see it. Okay, so that's what it is. This is the lamellar structure. So, you know what that means? It means that ring is made of emulsifier and fatty alcohol. So it's not like the fatty alcohol has to stay inside of the oil phase. This is giving you a mechanism that had nothing to do with Griffin's ideas. And so, I hope somebody could repeat this experiment using radiolabeled fatty alcohol, which will be a great way to know how much of that fatty alcohol is inside the oil phase and how much of the fatty alcohol has gone to do the rings. I will assume that the majority is doing these rings rather than inside. Now, one thing I need to tell you before I confuse everybody, the fact that you put the fatty alcohol on the oil phase to make the emulsions and you melt it there doesn't mean it stays there. So then, this is so simple and it's so beautiful. So it measures the rate of evaporation of water of the different emulsions. And you can see that some of them go very fast and so very slow. And it happens that the ones that have those extra rings lose water slower. So it is obvious that something's going on. And it comes with this image that we have seen a million times. So this is the first time somebody comes with an alternative to Griffin's method. And I say, I tell you something. There is an oil surrounded by all these rings. I have seen them, and I know, and that stuff is made of emulsifier, and my thickening agent, in this case, is a fatty alcohol. So there's a third phase. The third phase that does not exist on Griffin's method. The third phase that hardly the cosmetic industry thinks of it when you're developing an emulsion. So you go to a chemist working, well, I'm talking in general, making an emulsion, say, what's your oil phase? Oh, I'm using mineral oil. No, you can't use mineral oil. That's not natural. Oh, okay. I'm going to use isopropyl myristate. That's natural. Okay. Then what is your emulsifier? Oh, ethoxylated something. You can use ethoxylate. Oh, I'm going to use APGs. Okay. So what is the third phase? You say that's the problem. We think in terms of the oil phase or the emulsifier. And what is the third phase? There is 3 phases. So in this paper, the third phase is made, well, you can make an emulsifier alone. There is always an excess or a combination of the two. Well, is something else? So what happened? Okay, tell me what happened. Next, this professor is fantastic. I tell you again, I mean, everything we know, it comes, this, with the exception of the paper I just showed you, the rest is just come from outside the industry. So he lost this paper and he says, I'm going to figure this out. So this is the drawing, and this is, look at this image is 1980. He did an electron microscopy, and basically this stuff here, the rings, these are the rings. So this stuff here stays. Okay, like, it's so, I can't believe how good this is. So he says, okay, I'm going to send this submarine. It's a German submarine. And he said, I'm going to send it inside. I'm going to figure it out. What on earth is this? So in a stroke of genius, I mean, these guys are so brilliant. He says, you know what? I'm going to make an emulsion without oil because I want to know what these rings are made of. I just want to make the rings alone. And he decided to use an ethoxylated emulsifier and a fatty alcohol because the other guy used an ethoxylated emulsifier and a fatty alcohol. So this is what he does. So he blends the two together, cools them down. This is the melting point of this about 40, whatever it is about 50 or 60. You melt it, cool it down. I know what he's talking about because I repeated his work. And then you cool down, and you measure by XRD crystallography. And then he repeats the story, adding water. So what happens is that as water is added, the sandwich starts to open, and inside of the sandwich is water. This is his work. And so you can see, he knows exactly the atomic size, the distance, and the more water he adds, the more it's, but you see, this is the ethoxylate, this is the ether group of the ethoxylate. And so it's hydrating. As it hydrates, it uncoils, opens, and then opens the rings. So the rings there, he says, oh, I got it. So the rings are made of emulsifier and fatty alcohol, and there's water inside. That's great, man. So we know that it's not dry. And now he says, what happened there? That is water. Where the hell is that water? If I just told you the water is there, what is that water there? What happens is that when he had above a certain amount of water, you see the water is not trapped anymore here by hydrogen bonding. That water is free. Well, that's the way he explains it. So he says, okay, now I know. When I put more water than what those rings can put inside, it just overflows. And so you see, we have 2 types of water. It's chemically the same water, but physically it's not the same because this is water that is trapped inside the rings, and that's your regular water. Okay, you see, the same model explained clearly. He says, well, this guy says, I have water over here, but I have water over there. He knew the water is not the same because when he did that evaporation rate, he knew that the water was not evaporating at the same rate. So something must be happening. Now, this professor even goes and calculates of the total water, how much is free, how much is trapped. So in other words, how much is in here and how much is in here. But I decided not to, it's going to change. If you change the content of water, the emulsifier, everything is going to change. But the concept doesn't change. Not all the water is the same. And the reason why this is important is it's so easy to all see. Okay, so if you have lots of water free, but the viscosity is going to be less because the oil droplets are going to be able to move very much. When you put it on your hand, obviously it's going to flow because there is lots of free water. But the water that is trapped here is reduced in mobility. Okay, so look at the model is already telling you. And then hydration and the delivery of actives, because you see, the water that is trapped here is going to hydrate in a way different than this, because this water is free. This is water goes in and out. Whereas the water that is trapped over there may last us on the surface as a reservoir. And the delivery of actives, the same thing, because what you active is oil soluble actives here, water soluble actives is there. So, by the way, I'm teaching a course next month on the delivery of actives. I'm going to be using this model. So, there you are. So the first guy used fatty alcohol to thicken. This guy used fatty alcohol to thicken something else. Well, it did a variety of studies. So it used also, look at this, cetyl sulfate is your big brother sodium lauryl sulfate. This is an old paper, and until recently, cetyl sulfate was used as an emulsifier. Instead of sodium lauryl sulfate, which you know is not precisely the best thing on the skin, sodium cetyl sulfate is much milder, it's an ionic surfactant, so it used it the same way, and with fatty alcohol. And it also used soap, where you have sodium stearate and stearic acid, and it also used this one. So it used, here you have it, 3 different, he called them amphiphiles. I mean, this is the terminology that they use. I call them structuring agents. So the structuring agents used in these papers is the fatty alcohol, historical fatty acid, mainly with soap, and glyceryl stearate. All of them have one common denominator. And the common denominator is that they have hydrogen bonding that you need to trap water, and all of them are waxes. Waxes means they are solid, and therefore they are going to give you that crystalline structure in a solid phase, a solid state. Now, I'm doing fine on time. So, I forgot to say something. Look at this. According to most belief of the industry, glyceryl stearate is an emulsifier. According to this model, probably is not. So when we think in terms of how we make emulsions from the legacy of Griffin, that we only have 2 phases and that the glyceryl stearate is one of them, emulsifiers, that there is no 3rd phase. This is why it becomes so difficult to make emulsions. And then you have courses and seminars that teach you how to make emulsions and control everything in a couple of hours using the model by Griffin. You just can't. The model by Griffin is wrong, has been wrong for day one. I'm telling you, I give him credit for what he did, but not for his explanation. Did practically speaking. So here you have 2 papers, one from the industry, the other from academia, that are basically the same thing, a more upgraded version with more science than the other. Well, more science, the university professor goes deeper on the term. So I'm going to introduce you now Professor Eccleston, which is one of the other ones that has worked on this. And this paper was published in our journal. I tell you, the first thing I read this thing, I remember, I need to copy this twice, the paper, because you have the writing over here and the graph over there, you need to go back and forth. And there were like 20 pages. I started reading this thing, and about 5 minutes, I collapsed on the table and I almost died because this is so heavy. Holy man, it's so heavy. Now, she was invited to give a keynote lecture in the Congress of the IFSC. It's the only time that I know there has been a keynote speaker that talk about cosmetic science, emulsions as a science. The only time. Now, you see, this Professor Junginger has been using all these emulsifiers, anionic and non-ionic, ethoxylated. So she's going to do something completely different. He's going to use a cationic emulsifier. Excuse me, the question is, will the cationic emulsifiers that have nothing to do with the other thing will do the same thing? So he's going to use the same technique. So here's his cationic, cetrimonium chloride, and the structuring agent is the fatty alcohol. So it's going to do the same thing. So this stuff over here is made of cationic fatty alcohol. You get the idea. So it repeats the same thing. It's going to add water, and it happens the same thing. The same thing. And what makes the difference in the cationic, here we are, is that he could put up to 90% water, and she still got trapped water, all of it. So now you can see by the position of the peaks just says 1, 2, 3, cha-cha-cha, that means it's lamellar. Now, the peaks, the position of the peaks, chun, 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 tell you if it's lamellar or not. The height of the specific number, so you see, this is double that. That means lamellar. That there is the fatty alcohol is saying over there, hello, I'm here. Now, this tells you how high, the total content between the sandwich and the water inside. Now, hey, just in case you wondered. So a hair conditioner, from the first day we have them on the industry, is basically a lamellar gel network. That's it. And this cream is one of the few, I believe, by Johnson & Johnson that uses a cationic emulsifier. So there you are. What least expected in a hair conditioner, I think all the hair conditioners formulated with a cationic and fatty alcohol have that structure. Now, one thing she did is that introduce, I don't know if he was the first person, but I'm for sure that she did in this paper, the use of differential, well, you know, this technique. And you can see here how the melting point of let me use the word rings, that obviously varies. I almost remove this out of it because I want you to get the concept. The concept is that the melting point of those rings obviously are going to be related to the emulsifier that you use and the structuring agent that you use. Fatty alcohols have the lower melting point, fatty acids the highest. So depending what you use, you're going to have a different melting point. And now the importance of this is critical. Because imagine that you have a cream that it melts the rings at 40 degrees. Well, you know what happens when you do that? You're going to get 40 degrees in your skin. And here, it melts at a higher point. So this is why sometimes you said, take it. Wait, you're not going to guess anything if you just start mixing and you don't translate the the chemical composition into physics and identify the physics with this stuff. You have no way to understand this. There is no way. Now, here, the combination of the two, something as obvious as this, that the industry has known for more than 30, 40 years, is unknown by a large amount of people. That's my view. I'm teaching most of my students work in the industry. Now, all these techniques, we have them since the 1990s. Now, hey, okay. I just repeat this to you. If you want to see how a cream behaves, this technique tells you. I want to tell you that I took this away because all these techniques I have used when I was working with this model. So I didn't invented anything. All I did was to take bits and pieces from everybody else and use them for my own understanding. I need to tell you also that my students at the university, I explained to them of low-tech alternatives because not everybody has an X-ray diffraction. Now, in my case, we need to send the samples to an outside laboratory to do the analysis. Normally, you don't have an X-ray diffraction machine at your company, but these other techniques, for sure, this is more common, especially, I don't know that one, but optical microscopy, for sure you do. So here we have Griffin's model that is based on having emollients on the one hand. That's how you make an emulsion according to Griffin, right? So you start selecting emollients, you know the story. Then you check the emulsifier, any emulsifier for as long as it has the same HLB, and that's the end of the story. But look what happens with this model. It starts completely different. Do you see emollients there? Of course not. Because the model tells you the most important thing in an emulsion is the third phase. The third phase that does not exist in Griffin's method. The third phase that most people in the industry don't see when they're making a cream or a lotion, and is made of a structuring agent and emulsifiers. Those are the structuring agents. And you see here, what happens is that on Griffin's method, the structuring agents appear as components of emollients. There you are, the stearic acid, alcohol, or emulsifiers. And the model says, no, it's not. No, it's not. Are they more? Well, I don't know. Maybe there are more. The reason why I selected these three is because these are the ones that I see as part of the rings working as structuring agents. Now, all the stuff has been made with the classic emulsifiers that we have had in the industry for a long time. So that's why when you hear the new crystal, the new liquid crystal emulsion, the new emulsifiers that do all this, well, it is for you. All this work on liquid crystals and lamellar, which is a specific type of liquid crystal plant. Yeah, this is the lamellar. Here you have it, lamellar, with that specific X-ray diffraction pattern. I've been around for a long time. So we have these emulsions for a long time. So take a deep breath. I hope you're smoking, man. Okay. Oop. Don't get scared. These are all the emulsifiers, well, most of them, the way I teach them at the university to my students. And when they see this, half of them already died before we go into the details. Now, these are all the families. And within each family, we have subfamilies and subfamilies. And it used to, you wonder, oh my God, the fact is that when I give them an option of summarize this class or not, many of them, the majority, likes to write a summary because all of a sudden they feel relief that now they understand emulsifiers. And the reason for it is because the chemical name is the least of their worries. The most important thing is how physically that emulsifier looks. Well, this is a class about, this is not a class about emulsifiers. So anyway, so let me ask you something. So this is a fairly new paper. There you are, 2007. And you can see, this is fantastic, man. I'm so impressed. Look at this, check it. You can see the lamellar face, that's the old face. You can see the lamellar face, you can even count how many lamellars are there. So what emulsifier is this? I tell you what, an oldie but a goldie. This is PEG20 sorbitan stearate. You see, these all emulsifiers, all of them have been making stuff. So these are the ones that had been studied by the industry. So in case you wonder, so what happened to this other? The sucrose esters, the APGs, well, that's the glucoside ethers, they insist. Well, it is for you. They assisted. And originally, these are the ones that were used because the ethoxylation process from an industrial viewpoint was not that easy. So at the beginning, most of the emulsifiers that we were using were called, are called food emulsifiers because they are very safe. No, stuff is made with sugar and a fatty acid, so the human body knows what that is. So we have had them. The problem is that when they were used to make emulsions, they didn't work that well. And when the ethoxylated emulsifiers came, they say, see you later, alligator. Now, you know what's happening now? They're coming back and they're being presented as new. Really? I didn't know that. New. I knew it was the 1940. Okay, so what happens to these new emulsifiers? Well, to be honest, I mean, no, this has been around. This was also invented by GAF a long time ago. So I want to show you right now if these new emulsifiers build lamellar structures or not. Okay, well, this is acetyl phosphate. Well, this looks to me like a lamella. I mean, it doesn't have the detail of the other, but you can see a big crystal there. The sucrose stearate, I have been able to find any. This was published on Cosmetic and Toiletries, but I wouldn't be surprised if that also is a lamella. Okay, you know, you're seeing the wrong thing. Now look at this other. APG. All of them. All of them. And here I have even a taurate. Notice, I mean, taurates are used as surfactants that foam, but when you move from carbon 12 that foams to carbon 18 that foams much less, then it becomes an emulsifier. And you see, in combination with the fatty alcohol, because by itself it's gonna maybe not form in a lamellar, it forms a lamellar. There you are. So the fat 1, 2, 3, cha-cha-cha that blips in specific locations, it gives you the fat that is lamellar. And so is this other that has 10% cream. You see, it's chun, chun, chun. The position 1, 2, 3, we know that is a lamellar. Now, I tell you one thing, you're gonna be surprised. I wanna bring this statement again. It says, biometric lamellar creams for APGs. I don't know what you mean by biomimetic, but I can tell you one thing, there's no APGs on the lipids of the skin. There's no sugar, there's no fatty alcohol. Now, this surfactant will form a lamellar. It will form a lamellar with a fatty alcohol. And you know, if you buy, say, Montanov 68, or whatever is the name, it's a blend of APG, cetearyl glucoxide, and fatty alcohol. So you have the two together. You know what this is? Sodium lauryl sulfate. Hello. Sodium lauryl sulfate and fatty alcohol. I even talked to the authors of this paper. So this is a lamella phase. Will you put this on your skin? Of course not. It's sodium lauryl sulfate. So my point to you is that having a lamellar structure as a marketing tool has nothing to do a lamellar structure as a matter of science. So you can market lamellar if you want, and this is what I don't like, because we are transforming a serious scientific concept, the buildup of these emulsions that controls the properties for rheology, this and that, now are using it as a marketing tool. Like if only these emulsifiers are building these structures, why this for you? All of them do if you know what you're doing. So in reality, what the model tells you is that when you are formulating and you are looking at all these emulsifiers and you are going to be building all those structures, and I'm putting emulsifiers, I'm not putting here the structuring agents, you need to look at them not as a matter of HLB, for God's sake. It's a matter of how hard the emulsifiers are. What's the melting point? How do they trap water? Are they discrete or oligomeric? Tell me this. The students at Rutgers University, I bring them to the Middle Ages. This is me. Oh, look at that. Look at that. I was there on the Middle Ages. This is 1600. I was there already. And this is my assistant. He's the one that is getting burned. I'm not getting burned. So I explained them because this is the way I learned this. So I built all these rings by themselves using a variety of emulsifiers, well selected, structuring agents. I was building the rings. And as a matter of fact, that's an example. This is something I recommended to do. I have a variety of emulsifiers, including the ones that are non-ethoxylated, fatty alcohol, this and that. And I just say, okay, so this is how I teach them how to learn how to make emulsions. Now, somebody said, wow, this may take maybe 2 weeks, 1 week to do this. And I say, yeah, that's the problem with most companies. They can afford you to spend 1 week learning how this works, but they can afford you to spend 6 months developing a cream, trial and error. Come on, for God's sake. All right, so where's this stuff? Hey, Tony, this for you. I just put this for you, man. Okay, I want to explain to you something that makes ethoxylated emulsifiers unique. So anything here that is based on ethylene oxide has an oligomeric structure. I want to show to you what it is. Discrete means you have molecules. If I tell you sorbitan laurate, that's what it is, one molecule. So you may say, well, sorbitan may have a little impurity there, but sorbitan laurate is one structure. But when you go now, and you use these two very common emulsifiers, what happens is that STRF2 is not one molecule, it's a blend of molecules known as oligomeric. So this means that, well, that's the distribution of the oligomers. So what happens is you have a blend of oligomers. The oligomers are, some molecules have one no ether, others have one ether unit, other 2, 3, 4. So it's not one molecule, it's many. The average is 2. So that's the distribution. So when you blend the two, what you are doing is ending with a homologous blend of molecules that we perceive as 2 molecules, but in reality is a blend of all these oligomers. I don't have the time to go into more details. Now, one of the greatest things about the Griffin method is that it tells you that a 50-50 blend of STRF2 and 20 is the same thing as STRF10 until you plot the oligomers. So anybody that has made an emulsion knows that it's not going to be even close. And the reason for it is because these materials are oligomeric. And the good thing about being oligomeric is that even if you don't know chemistry, and I tell you, when Griffin saw this, he didn't know what the answer was. He should have known, because the oligomeric distribution, while experimentally was not there yet, theoretically, people knew that these emulsifiers were, from a theory, because the synthesis process, the kinetics were oligomeric. So when you are blending these two emulsifiers in different proportions, all you are doing is changing the oligomeric composition. And it happens that this line means here is the oligomers that are more likely to love the oil phase, whereas all this other portion is available to build those rings. So now you can see when you change, well, you can see it's quite a different story. And the beauty of this system is that that is what you get with one oil. If I now change the oil phase, that changes. So the reason why this stuff always works is because you have two, you blend different proportions, doesn't matter what the oil phase, the emulsion works. Why? You're not doing anything. You're not doing anything. They do for you. The oligomers do it for you. You may need to use more, you may need to use less. So that's it. That's the reason behind the beauty of any ethoxylated emulsifier. So all of a sudden, that's against the ethoxylated emulsifiers. So we need to remove them because we have a problem with 1,4-dioxane, and we need to remove them and replace them with natural materials. Okay. All right, so let me see this. So APG, my favorite. Oh, by the way, APG, consider the sensitizer of the year a couple of years ago, is made of fatty alcohol and glucose. And this one, you know what it's made of. So I guess this is natural, this is not. But I have news for you, because Corolla, that I know, makes it all from natural resources. So STRFX is as natural as that. What is this stuff? What is this stuff? So, I love this thing. Now, this is a paper written in a Italian university. Hello, buongiorno. And so they have 3 oil phases, and they're going to make a total of 9 emulsions because they have 3 oil phases, 3 emulsifiers. And that's the structuring agent. Now, by the way, this article, which is fairly new, it's 2015, I think. Anyway, is build emulsions according to Griffin. So they can explain nothing. They can explain nothing because with the Griffin method, don't explain anything. It happens out of luck, that fits into what the model tells you. And so the model tells you to do a magic thing I will need to show you in a moment. And so I can explain the results because it fits into the model. And I tell you, the students are coming back, the part number 2 of my course, I'm going to be giving this paper, and I'm going to ask them explain the results of the 9 emulsions. They're going to die, man. On the sensorial evaluation, the winner was that. The winner was that. Defeating APGs. And in hydration, I mean, they took that formula, they checked for hydration, and look at that, 47% increase of hydration. The control means no cream versus cream. Look at that. I know why it's hydrating, because there is all this water that is being trapped on those rings. You may say, oh, what about the dioxin? Well, that's the amount of 1,4-dioxin, my estimate, based on the composition of emulsions per every gram. So 1 gram of cream has all those grams of 1,4-dioxin. And not only that, natural dioxin. So what is this stuff? What is this stuff that we are just propagating that is not true? Whoopa, I went the wrong way. So anyway, I'm probably the only person in the industry that is trying to put an order in all this misinformation that is going on about ethoxylated emulsifiers. Now, this is about the Lamellar Gel Network, but I happen that are fantastic to build the Lamellar Gel Network. And so in July and then September this year, I'm going to be talking about this, assuming they let me talk again. So, all right, take another deep breath. I hope you still have the cigar. Okay, those are the official names. All right, there's no more names than these. So any other words that you heard over there are just marketing stuff. I see names of all sorts. So, okay, start here. This is your basic block. So this is what those 2 persons did, the guy in Japan and the guy in Germany, I think he's German professor, they built the block by mixing emulsifier and a structuring agent. You can do it with emulsifier alone. And that's the basic code, and it's called alpha gel. Don't look at me, I didn't put the names. When then you add the water, that's called from alpha to beta, that to do with crystallography. And then finally, when you add the oil phase, that's the network. There's no more names. So anytime that you hear anything, now if you were to remove the names, forget the names. It is so obvious, it's so beautiful. This is your Lego. And then you put water, and then you make the emulsion. End of the story. I mean, that's how it goes. It's no more than this. 12 p.m. Oh, I have 5 minutes. 5 minutes left. Okay, now, this is supposed to finish now. Now I'm going to go into a bit more advanced. So I hope you don't go anywhere because, you're going to love this thing. Okay, now. Okay, so you see, the X-ray diffraction allows you to see this. So, and by the way, this is my work. I tell you, I did this. Well, I did this, the machine did it. I did the motion, I took the machine, so I can figure out this. I know this is the height. And then if you notice, there's this thing. So what happens is, let me show you this. Say, assuming I am looking at the emulsion like this, so I can say, yeah, the box, there you are. So if I look at the emulsion like this, the X-ray from this distance, tell me how close this is. But if I look from here, I can't see the composition of the crystals from the top. To do that, what I need to do is to look over. Well, I don't look over, the machine does, it does like this. So what the machine is changing, all of a sudden, I'm gonna be able to see the top. So I will see how those crystals are organized. And there you are. They are organized like a hexagon. So what you have here is, for example, you can see here 6. So we have, imagine that is emulsifier, 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 boom, emollient. There's one unit on the middle. So if I make this emulsion and I only use STRS10, so I represent it this way. This is the stearyl and this is the ether group. So I have those, all of them are the same. Huh? All I have there is just one ingredient. If I now use a different emulsifier, you already got it. Look at that. This thing melts at 45 degrees. This melts at 65. This is soft. This is hard. Are you telling me these two emulsions are going to be the same? According to Griffin, yes, because they have the same HLD. What I use for you, according to the model, no. I know exactly what it's going to be, this versus that. I don't need to be a genius as I am to know what the difference is. I know what is going to happen. Now, imagine now, because I consider this emulsion, I might for a moment, I don't have enough texture. Well, okay. So all I need to do now is to add a structuring agent. So I'm going to represent it with this, so I can see, that's it. So they don't form one crystal over here, one crystal over there. They form a mixed crystal, like a mix myself. And so it's just a matter of the proportion, you see? So now, depending on the ratio, so you use only an emulsifier or a blend, you always get the lamellar gel. And water inside, there will be different properties, because obviously not all the emulsifiers, not all the structuring agents are the same. And look this, so what you have here is what happens into this system. Well, you can see yourself, I don't have to tell you anything. So in this specific, whatever there are, I want to tell you what emulsifier, what structuring agent is. I want you to get the concept. You can see how you can alter the rings. And this is what I teach my students, by the way. Now you can see this is done with a polarographer that, well, you can see the impact of the rings. So this is to do with Griffin. The model is telling you the more crystallinity, the more is going to blip in this unit, and you know exactly what the field of the emulsion is going to be. So, okay. Now, for those of you that went to chemistry classes when you were younger, I need to tell you that chemistry works in moles. So, you know, when they ask you how many grams of hydrochloric acid you need to react with sodium hydroxide to get salt, you say 1 gram, 1 gram. We say 1 mole, 1 mole. So chemistry is based on moles. And so don't get easy. So if I say I make an emulsion with 3% of STRS10, that's the average molecular weight, that's the number of millimoles that I have. So all the sagons of the crystalline structure are going to be the same, and I will have, that's the number of millimoles. So let's assume that that represents 4 millimoles. Okay, now I have not enough viscosity. So what I'm going to do is I'm going to do fatty alcohol. Now, according to Griffin's method, this is going to thicken because it's going to thicken the oil phase. And here for you, that's not what the model says. What the model says, no, this material is going to be used now to build the rings. And if I now do the 4 divided, oh, look at that, 16 moles. So even though this is 3 and 4, they're not far apart. Look at number of moles, 4 and 16. So holy guacamole, that explains why the viscosity increases. That explains why the texture changes. Because what you're changing is the number of rings that you have around the oil phase and the hardness of the rings. So all of a sudden, you have 5 more times. Because we work in chemistry and the molecular weight of the fatty alcohol is much less than that. So by weight is about the same, but not by chemistry. That's the beauty. So that's not a problem on the model. You need to work as a chemist, not as a mixer. We have plenty of mixers on the industry. Yeah? And also remember the molecular weights of the emulsifiers change. So in this case, if I put the same thing of these, I double the number of moles. So you need to always, as a chemist, you know, chemists work with moles, to the best of my knowledge. So what is the molecular weight of carbon? 12. What is the molecular weight of nitrogen? The same, right? No, you know, that's not the way chemistry works. So in general terms, the molecular weight of emulsifiers goes from 300, probably soap, to as high as 1,000 or higher, depending what you're using. And so this is what happened. You use the same amount. Look at the difference. So when you say I'm using the same amount of emulsifier, that's not true. When you're looking at a formula, according to the Lamellar Gel Network, the percentage needs to be translated into moles as far as it goes for the emulsifier and the structuring agent. Moles, no percentage. And don't get dizzy now. Yes, I'm gonna die with this one. Get ready, sit down on your chair. Okay, so I'm telling you right now, all these are hexagonal rings. So you have here in this hexagon, yeah, you have an hexagon here, right? So what I have, my hexagon is awful. 1, 2, okay, you know the story. I got dizzy doing this. So black is the emulsifier, white is the structuring agent. So if I change the ratio, well, you see what I'm trying to say. That if these are the legs of a table, the table with 6 legs, well, you can alter the ratio. Needless to say, the strength of this, you're not going to see the strength of that. So that's what happened. As you are moving the proportion, you're changing the composition of the rings. So what happened if we go above 1.6? Why do we stop at 1.6? Well, because if you have an hexagon that has 7 things, 1, 2, 3, 4, 5, 6, 7, the total is 7. You said one on the center is the structuring agent, and 6 is the emulsifier. What happens if I put more? So if you put more, you need to knock out one of the emulsifiers and put the structuring agent. Okay, see what happens. This is what it is if you do not go over. So all are forming the alpha gel. So you have emulsifier, the structuring agent, whatever is the order, and you have the water drape inside, and that is how your emulsion looks. If now you go over, look at this, man. It's fantastic. Your fatty alcohol excess cannot crystallize inside of here because there is no room for it. You just knock out all these potential spots. So this is called semi-hydrate, you see? And if you notice, there is hardly any water inside. This is plenty of water. There is no water here. So it's called semi-hydrate. Other people call it co-gel. So it crystallizes different. And it has the tendency to precipitate in some emulsions because to start, no flexibility. You can see some flexibility here. The water is there. It's called gel precisely because of that, because it has some flexibility. Whereas this is harder. And by the way, the specific gravity is about 1.1 something higher than water, so it has the tendency to drop. So the problem, listen to the model. For as long as you're operating on the model within the ratio 1 to 6, you're going to get a direct correlation between the changes and the performance. You know what you get from the emulsifier, you know what you get from the structuring agent. If you're changing the ratio, all you're doing is changing the number of legs within the table. You can predict what is going to happen. As soon as you go over, you're creating a different structure. All of a sudden, say, it doesn't work anymore. Yes, it does work. What happened is that now you have a different structure that does not have the same physical characteristics. So that's why you are beautifully easy to go if you keep this not above 1 to 6 by moles. So that's how we know it. So the S-ray diffraction allow us to see, this is the hexagon, and the distance is 0.42, here is shorter. Now, one more thing, and this is practiced by the industry probably without knowing anything about the model, is that if you are going to have this problem, and you are going to have the problem potentially if you go above the 1 to 6, the one way to stabilize is putting one of these thickening polymers or polymeric emulsifiers, and that what we're going to do is stabilize the system by different means. So which is the best? Well, I'll tell you one thing. The one that we have the least work is the fatty acid, probably is reduced exclusively to soap. Don't forget, this is a model that has been built based on information we have. This is not a model that Tony Olenek and I get up in the morning and decide to make 100 experiments to put the model into test. No. So the one that is very dangerous is this one. I have very little on it because glyceryl stearate, as anyone that has made emulsifiers or chemicals know, is a difficult thing. It could be, it varies the ratio mono stearate to distearate, free stearic acid, then some stearic acid neutralized with soap. So glyceryl stearate can be anything. So finding something consistent, it becomes very difficult. I have something, somebody did some work in Mexico together, and we went all over the place because the emulsifier glyceryl sterate was a blend of all kind of stuffs. So most information is with the fatty alcohols. Excuse me. Doesn't mean the others that don't work. I'm telling you what the information is available. Now, this gentleman, and again, from the good old days, 1976, for God's sake, the days that were the industry, excuse me, was doing something. So he decided to study what you have here. So he took an emulsifier, that we make an emulsion with an emulsifier that is liquid. Now, this is before the days of the model. So this is a liquid emulsifier, and he tried to get viscosity adding these different fatty alcohols. So listen to me. This is now, not when he did it. He didn't know this. It happens that he was using with a ratio above 1:6. So he made an emulsion with an emulsifier that is not that strong, tried to harden the rings by adding a fatty alcohol, use a variety of fatty alcohols, and it went over the magic ratio that the model tells you don't go over. He didn't know. There was no model at that time. So what happened? Hey, this is what happened. So you see, it happens that as soon as you go below a certain temperature, the possibility of these crystals, because they crystallize in a different way, to pop down happens at 16 degrees here, if you only have carbon 16, 45 degrees in carbon 18, and you can prevent the problem going all the way down to 10 degrees. But that was in the specific conditions of his formula. So what this says is if you go over carbon 16, 18, better, excuse me, the ratio 1:6, better be a blend of the two. That's why cetearyl alcohol or a blend of cetyl alcohol, for reasons that are known or are known by the formulator, is your best bet. You see it over here. Oh, there is an explanation as to why this happened on the paper, on the chapter that I told you. So these are the 3 rules, fantastic rules for stability. So you don't need to make the formula and then, did my plane will fly? Did my boat will sink? Self-explanatory. Self-explanatory. And the 4th rule, I add that one as my contribution to the model. And a little bit, I mean, that's not unusual today to see, especially with the new emulsifiers, polymeric emulsifiers, you can add a pinch, a little bit, 0.2%, 0.3%, and this is great. So you can make emulsions that have only the polymeric emulsifiers. At the other end, these ones. And then you have something in the middle. And the one in the middle is if you combine the two. Now, what I'm telling you in this case is you can always make one this way, which is basically emulsifier, structurization, and oil, and add a little pinch, just in case that you go over and that thing is going to pop down, the fatty alcohol. Oh, this is one fantastic part. I want going deeper. So I saw, can you go through the wall? This is the wall that separates Canada and the States. So can we Canadians go through? No, you can't because the border is closed. So can you just go in? I'll tell you what happened. This is so nice. Well, the answer is yes. When you make the emulsion, all we have done right now is to assume that those rings are based exclusively of the structuring agent and the emulsifier. But I can tell you right now that depending on the oil that you use on the oil phase, and depending on the specifics of the emulsifier and structuring agent, you can have one of these molecules entering on the wall. And this is a beautiful thing. This paper is fairly recent from a university professor. And so you can see the same what you see over here is the same emulsifier, the same structuring agent, and all you have done, they have done, is to change. This is a capryl, this is a triester and oil, and this is a hydrocarbon branch. Well, you can see the emulsions are not the same. And they're not the same, no viscosity. So what the professors said is, well, imagine that this is what you get with emulsifier and structuring agent. That's it, that's your lamellar thing. So when they made emulsion with the hydrocarbon, by X-ray diffraction, they see that this hasn't changed. So this specific one, in this case, nothing happens. Well, when they use the other one, they see by X-ray that something had happened and that this thing has penetrated there, you see? Now, I am going to show you their X-rays because I did the same thing before this paper was published when I was doing my work. Let me show you this. This is my own work. So, and this is my own, again, my own X-ray. I mean, I send it outside to have the X-ray. So this is the peak. This is the lateral packing. I know that I have here is a hexagon made of the two, and whatever the proportions are irrelevant. So I could be 1:1, whatever it is. So that's the peak. So now this is for it. This is my own work. So now I go and make the emulsion, complete emulsion. So if I put emulsion A, nothing happened. Okay, I found no difference. But when I put a different emulsifier, holy guacamole, it changed completely. So you see, now, in addition to the peak, the same peak, there's another one. What the heck? So what happens, you see, that's what happens. So actually, we have, when you see the peaks, this is three possibilities. This is the one that comes from the excess fatty alcohol. And this is the one that comes if you have an emulsifier that is liquid at room temperature or not at 30 degrees, or when a liquid emulsifier goes inside. Look what happens here. You see, this one can only rotate. So it just turns around. I don't want to turn around because you see my bald head. So, you know, here I know what it is. So this is it. So that's what it gives you, that beautiful flexibility of the alpha gel, because the molecules can be dancing all day. If now you open the ring a little bit on the X-ray, what happens is that not only but this. So you can see now in terms of viscosity, this is going to be less viscous, more fluid, because the molecules in this hexagon not only can rotate, but they can do like that. So they can be, yes, it's so great, man. And this, by the way, is the tightness. So you can see that these are three possibilities. In my work, three different sensorial aspects. So these are all the possibilities that you have. So one part, the first thing that I told you is the alpha gel, you know, the water trapped inside. Then the question is the details of the rings. And the details of the rings is the ratio between one and the other. Then this is what you would like to have. And obviously, if something penetrates inside, you're going to have more fluidity. So the model is guiding you. Now, I don't expect everybody to have an X-ray machine waiting by, but the model explains to you why certain things can happen. Let me see. I'm doing great. 2 more minutes. Okay, this gentleman happens to be from Mexico, and is a chemistry teacher on prep school. I do not know him personally, but I want to use him as an example. I gave a webinar last year, a seminar, on this model for Latin America, and he loved it. And he said, I would like to work on this. Now, he has his own cosmetic line that makes at home. It's all natural. It's homemade. So he has been working with doing some experiments, and he has come up with the alternative Lamellar Gel Network, the Mexican model. You can see this, man. He just moved around. Hey, Juan, you can put that thing over there. Let's go the other way, man. So anyway, he's going to be making a keynote speaker presentation on the upcoming IFSCC International Congress in Cancun. He's going to present the Mexican model of the Lamellar Gel Network. Oh, man, I love you, man. So listen, great work. This is very, very nice. Because what happens is this. So he made this emulsion at home, but you can see this is, I mean, look at that. This is his home. This is his homogenizer. And this is he makes the emulsion hot, and then he cools it down. This is an improved version because he normally uses a wooden spoon, but for this presentation, he decided to put a glass rod. So he just made the regular emulsion. And okay, that's what he gets. But nothing unusual. But now this is what we did. So what happens now is that we're going to make the emulsion a different way. So listen, so he made what according to what happened in the past. So he makes the emulsion with no oil. No oil, he's just making rings. Now, you're processing everything the same. You're making rings, and now you cool it down. You wait for 2 days, because you know, when you're making emulsion, I forgot to tell you this. When you're making emulsions with rings and water, you never know what the viscosity is for a couple of days, if no more. So anyone that listens to me, you make anything according to what I just told you, wait for at least 48 hours. You need to give time to the rings to stabilize, to the water get trapped, 48 hours. Don't put anything on stability for at least 1 week. One of the biggest mistakes I see, people make the emulsion, okay, at 3 p.m., they're finished, they put on stability. Don't do that. You cannot do a stability test until the emulsion is in a stable state. And it takes at least 48 hours minimum, and all the way up to a week. How do you know that? Well, check the viscosity every day. Taste the texture every day until it stabilizes. So anyway, so he makes the stuff, waits for 2 days, and then puts the oil inside. And this is what he got. It's not the same. It's not the same. Look at this. It's the same chemical structure, but the physics is not the same. And then it changed the oil. This is maragula oil. And look at that, completely different. So what happened according to this, is that this is your standard. Exactly, I had 2 minutes left. This is your standard thing. This is different. So what it has been done in this case is, this is from scratch. This is what's going to happen. Everything is in a melted state, and as you cool down, you form the rings, cools down, let it stabilize, trap water, free water, God bless America, everything. This is a different thing. What he did first is this. He made the sandwich, the bread, and then he put the oil. So what happens now is that the oil is going inside the sandwich. It's obviously not the same. That's why the viscosity is not the same. So the Lamellar Gel Network gives you the opportunity to make emulsions in another way. So basically, you can have the stock of the Lamellar Gel, and then you say, oh, today I feel like, hey, that's what he's going to do in his house. He's going to open this store over there. I'm going to go with him. And we're going to have there your Lamellar Gel. And then we're going to say, what would you like to have? And the lady says, I would like to have calendula oil. We put the calendula oil. Next, what would you like to have? Here it comes this guy, mineral oil, because I am anti-natural. So that's what, right, seriously, this allows you to have a stock of the Lamellar Gel, and then you make the network by adding oil. There you are. I'm happy to see that there is a good number of papers that are now being done. This is a selection of them, excuse me, that are based on studying emulsions according to this model, not according to Griffin. This is fantastic. Well, there are still papers according to Griffin, hey, including decimals for the HLD. I'm happy to see that. And the reason that I'm happy is because, as you see, I told you before, there are holes that we cannot explain. And that's why new papers are welcome, because this is a model based on papers. Whatever papers you have are the only thing you can use. But in my view, the industry is missing the equivalent to the genome project. So there has never been, because this model is not based on an experiment by someone, the experiment is missing, where we will have what I tell the students to do at home. I can do it now. I don't work in the industry anymore, which will be to do all this. Now, I don't know how long it took the genome project, whatever it was, 10 years, 5 years, I don't know what it was. But look at the benefits. They do the vaccine in 1 week. So this is the problem. The industry should, I'm quite sure that some companies may have this. So the genome in this case means we need to know this. We have been relying all the time. All you need to know is this, the scales from Griffin that do anything. So now, that's the story. Now, as I told you before, initial and final. Now, the reason why I put these 2 dates is because when I was ready to retire from the industry, did I put the right name? Yes. I presented, I think I confused the dates, but it doesn't matter. No, it's before that. It was 2010, 2011. I made a mistake. So those are not the days. It's before that. I sent papers to 2 congresses of the IFSCC with this stuff, some of the stuff I showed it to you. And they said, no, this is of no interest to us. And that's my bitterness. So I came to an end. So I bring here Antoine Lavoisier, including a cat. That's not part of the picture. Okay, so somebody put a cat. So what I think is that the industry needs, emulsions as physical chemistry, needs to have a congress. I discussed this before with my friends at the AOCS. And if we want to progress and fill the holes of the model, I think we are going to need to rely in something else other than the IFSCC, because they're not interested in this stuff. So it would be great if we were to have a congress, a conference, not congress, a conference where people talks about stuff, a conference on emulsions exclusively as physical chemistry. Nothing about natural and sulfate-free, and no. Physical chemistry. Carbon-based, silicon-based. There's lots of stuff still. Okay, I have finished. That's it.
Well, thank you. Thank you for your presentation. It's been fantastic. One of the comments I'd like to pass along to you is one of the people said, Dr. Ricardo is great and has a very high passion for the technology, and they are very grateful for your teaching.
Thank you.
Couple of quick questions, if I could.
I only like those comments. Don't ask me any questions, man. Tell me more comments that I'm great. No, ask me no questions, man. Okay, go ahead.
Quick question on the effect of electrolytes and order of addition in preparing LGNs.
Yes, and if, obviously the order of addition makes a difference. I tell you, yes, the answer is yes, both. Because, for example, if you have ethoxylated, well, you know this, Tony, if you have, consider ethoxylated emulsifiers, the cloud point of ethoxylated emulsifiers is affected by electrolyte. So that's one possibility. Also, when you do especially cationic emulsifiers, the electrolyte has an impact. And the only thing you can do is investigate. So the answer is yes, it's a variable. And I like the question for a reason. The most difficult thing when you're making anything is to know what the variables are. And I'm telling you right now, the order of addition is a variable, because you can make the emulsion the regular way is you put the water and you add the oil on top, correct? Because in most companies, what you have is the propeller is here. So you can start with the oil phase, because then the propeller will be over the oil phase, the propeller, homogenized. So the regular way is water and you put the oil. But there is another way, which is you put the oil and then you put the water. So you can see from the perspective of the emulsifier and the structuring agent, they are not going to be on the same equilibrium when you start one way or another. Or you can mix the two. As a matter of fact, on the advanced course that I give at Rutgers, I consider this. It takes 2 hours to explain this. So yes, there is a variable. And so is the electrolyte. Yes, there are variables. And the more variables you know, the better you are. You need to experiment with variables. Good. Thank you. I can be more specific.
Thank you. So, I think what we'll have to say is we'll have to get you back another day, because there's so much more to talk about. We still have a lot of people in the room, so everybody was very interested in what you had to say.
Thank you.
We will continue along and hopefully do something in the near future and getting together a program. And thank you for your presentation.
Thank you.
And thank everybody for being here. So with that, I wish you a good day.
All right, thank you. Bye-bye. All right, let's disconnect. If I